Hi everybody, we're looking at Glacier Notes. And if you're noticing, yes, my hair is different. I cut it this morning. So I did it myself, so it's what it is. All right, so we're going to do a little bit of reading, a little bit of talking, but this is some of the basic facts that we need to make sure you get through, so here we go. Definition of glacier. It's a large mass of ice that moves slowly over the land. There are three types. We have valley glaciers that flow down a valley. We have continental glaciers that cover a continent, and we have ice cap glaciers. That's like the North Pole. The South Pole is over a continent, so that's actually a continental glacier. If you're looking at Greenland, that's a continental glacier. If you're up in the mountains, those are going to be valley glaciers. So an alpine or valley glacier is a long, narrow glacier that forms when snow and ice build up high in the mountains, and the valley glaciers are found with the ice flowing downhill because gravity is, remember, what is the source of all mass wasting. Everything goes from high to low. So the flow of that downhill where snow and ice accumulates through the mountains in the existing valleys, and then as it gets too much and it starts to flow under its own weight, it travels down and can create V and U-shaped valleys. A lot of times V-shaped valleys are river created, and U-shaped tend to be more of the glacier created. Continental glacier then is a glacier that covers much of a continent or large island. And today, continental glaciers cover about 10% of Earth's land, including Antarctica and most of Greenland. Basically, these are large ice sheets flat to the ground, and they flow outward from the place where the greatest amount of snow has accumulated. This is, I believe, the South Pole, if I remember my pictures correctly. This is a continental glacier, and this is where it would meet the ice. And you can, if it calves off, and that is what it's called, calving of the ice face, you get an iceberg. And here are the little melt parts of Antarctica. This is the ice cap. This is the movement of the ice cap from the 1980s to 2010, and we can see it changing, and it grows and shrinks throughout the course of the year. And as we get closer into 2020s, you would see that this ice cap is reducing even more than it has here. So our ice cap at the North Pole is shrinking. This is an aerial photo of ice cap. If you really want more terminology, you can go look here on this link if you go into the notes. And remember, you can always go back and look at these notes on your own time if that helps you later figure out any of these terms. Many times in the past, we've had continental glaciers that covered a good part of Earth's surface, including here in Minnesota. These times are basically known as ice ages. We're technically, we have all this warming going on, but technically we're still in an ice age. For example, about 2.5 million years ago, continental glaciers covered a third of Earth's land. The glaciers advanced and retreated and melted back. The last retreat was about 10,000 years ago. Glaciers can form only in areas where we have, and this is important, more snow falls each year than melts in the summer. So you have to have more snow accumulating in the winter than can possibly be melted in the summer. And when that happens, then you don't have ground exposed the next winter, and more snow accumulates, and we start to have the formation of a glacier. In mountain areas, snow builds up year after year. The pressure of the weight of more and more snow compacts the snow at the bottom into ice. And you saw that in the video. It's called neve. So this is important, this is a good test question. Once the snow depth of ice reaches about 50 meters, gravity begins pulling the glacier downhill. Valley glaciers move or flow at a rate of a few centimeters to meters per day. Sometimes valley glaciers slide down more quickly, and that's called a surge. And continental glaciers can flow in all directions. Valley glaciers go downhill. Let's take a quick look. I'm not sure if I'm going to show all this, but I do want you to watch part of this.
The Jakobshavn Glacier on the west coast of Greenland. It's a familiar destination, but it certainly looks different every year. Yesterday, Operation Ice Bridge returned to the glacier for the first time in 2013, repeating a high-priority mission they've now flown for 5 consecutive years, and collected another trove of valuable data and some great images. What's so special about Jakobshavn that keeps Ice Bridge and other researchers coming back? Well, it's one of the fastest-moving glaciers in Greenland. It produces more icebergs than any other northern glacier, and over the past 150 years, it's been retreating dramatically. Studying how glaciers like Jakobshavn are changing from year to year helps scientists get a handle on both the movement of the ice on a local scale and ultimately how much these glaciers might contribute to sea level rise. While studying the upstream catchment area of the glacier, kind of like the drainage basin of a river, was the primary objective on yesterday's flight, making a pass over the calving front of the glacier is always a highlight of the mission, as we can see from this video taken last year.
So that's ice going
Here
in.
we see two
to
views
the
of
sea.
the calving front from this year, with laser elevation data above and high-resolution photographic data below. And here's a closer look at just how detailed that imagery is. Icebridge plans to be back at Jakobshavn next year. Past, present, and future Icebridge flights over regions like this one are aimed at building a continuous record of change in Earth's polar regions to bridge the gap between NASA's ICESat satellite and ICESat-2, scheduled for launch in 2016.
Okay, so this is where we're getting into the erosion part of glaciers. So the movement of a glacier changes the land beneath it. And although glaciers work slowly, they are a major force of erosion. The two processes by which glaciers erode the land are called plucking and abrasion. Abrasion is those scratching, and plucking is literally you pluck rocks off and detach them from their bedrock. So as if I'm going to read the green part, as a glacier flows over the land, it picks up rock in a process called plucking. Plucking can move huge boulders. So what happens is you get the glacier maybe going up over a ridge, and then down here you actually get a little bit of low pressure behind it, because all of a sudden this kind of goes over it, leaving some space, and that low pressure starts to crack, and the air force above it can crack until you get these rock fragments actually breaking off, and then they get incorporated up into the glacier. Plucking is a good test question. Make sure you understand this process. Abrasion is as these rocks get picked up and they go over the floor of the canyon, they literally can scrape the bottom. It's just like using sandpaper on a table. You're going to scratch it up. Well, this is 2 miles of ice, and it's heavy, and it's got boulders the size of buses or bigger and smaller pieces, and they're getting pushed along and they're scraping the bedrock, and they can polish it. You can actually see polished areas where glaciers have come through. So many rocks remain on the bottom of the glacier, and the glacier drags them across the land, and that process is abrasion. Gorges and scratches on back, it basically gorges up big chunks and it can scratch, and those are our striations that we've been talking about for quite a while. So abrasion is the scraping across and making scratches. Plucking is water going into cracks and freezing and causing frost action and wedging to happen, and plucking off as they get cracked out of the bedrock. These are our striations. They are the scratches left behind, and you can literally follow. They're going to scratch in the direction of flow that the glacier went. So as you follow this backwards, you can literally walk back towards where that glacier started flowing outwards from. If you see scratches like this in rock, and you will see them in Minnesota, these are glacier erosion processes. They were scraping down these rocks. So a glacier also gathers, as it plucks this rock up, huge amounts of soil. Basically, we scraped a good chunk of Canada clean and deposited all that till down here and around a lot of the northern part of the United States where glaciers formed. So it picks up rock and soil as it moves, and when a glacier melts, it doesn't retreat backwards and bring everything back with it. It melts where it is and drops everything suspended in all the ice and snow, and drops it, and that dropping is till. And if I go by the official, mixture of sediment that glacier deposits directly on the surface is called till. And there can be tons and tons of boulder and gravel and sand and clay and silt and anything in between there. So this is glacial till. It's not sorted evenly. It's just dropped wherever it was. And the till deposits at the edge of the glacier. So sometimes it kind of pushes around on the side. And if you get these are called moraines, the place where it's actually pushed till out. So lateral moraines are actually on the side as it kind of pushes everything out to the side. The moraines that are in front of them are called terminal moraines. And a termination is when it stops, right? If you terminate your employment, you stop working there. Where a glacier terminates is where it stopped advancing. So we know that this glacier has surged a few times. The farthest it went is this terminal moraine. This terminal moraine has to have happened after this one, because guess what? It wouldn't be here if this was the newest one. So a terminal moraine is the point at which a glacier stops pushing and it melts backwards. In other words, it drops its suspended load and the glacier melts. Now it can surge again the next year. This is, you'd see these where you see summer. Now sometimes maybe this has a huge snowfall that next couple of years and it surges farther and you could actually have a new terminal moraine. But this would be the older terminal moraine. This is the newer one. And if it's on the sides, those are called lateral moraines. And we see moraines. Moraines are very common in our Minnesota landscape. Eskers are underwater ice rivers. They leave behind long, winding ridges of sacrificed sand and gravel. So now imagine a glacier underneath, and it starts to melt. And as it melts more and more water rushes through, it melts more ice. And so literally you can have channels at the bottom of a glacier as kind of an escape route for all the water farther back as it moves downhill. And with it, it's also depositing and pulling out as it melts all that sediment and sand and gravel and rock. And you can literally see, this is an esker. This is that underwater river at the bottom of the glacier that everything was funneling to, and it deposits these bigger hills of till. But when there are these weird winding shapes, that was more than likely a water meltway underneath the glacier, and that's called an esker. And I mean, look at this. It comes all the way back here, branches off here, and then comes down and makes a turn. They don't have to be straight, but that is an esker. Here is an esker going through here, meltwater. And if there's a big cavernous spot in the middle of all that till that really didn't have a lot of till and it melts, you can be left with these big depressions, and we call them lakes. Prairie potholes, another features, and if you go to Taylor's Falls, Interstate Park along the St. Croix, there's these featured called prairie potholes. They are low depressions in till that were formed by flowing water of continental glaciers. You're going to actually watch a video clip where we look at a glacial lake. Well, our glacial lake was called Glacial Lake Agassiz. And basically think of a huge amount of ice with a big melting lake in the center of it. As it keeps melting and melting, the only thing holding that water back is an ice dam. And if that ice dam melts, it can release the same amount of water as like trying to release 2 Great Lakes at one time. Now imagine how much erosion a river can do. Now make that 60 times, greater than like the release of the Amazon River at one time, and you can get these prairie potholes. And what happens is, and this happens in rivers, and there's a video that you probably have watched or are about to watch where it shows them currently forming in just regular rivers, and there's little holes. And as water moves down, it can move rocks and gravel, right? And sometimes they get stuck in that hole, just like this is here. And then there isn't enough force within the water to lift it out and pluck it out and keep it going. And they get rounded and smooth because within that hole, you get these little eddies of water that swirl around, and then more gravel falls in, and they literally act like a mortar and pestle, except we're grinding away the rock. And all of this wears down and down, and they can be huge, like you can fit in them. But this one is big enough you could fit a bus inside of it. So if you ever get a chance to go to Interstate Park, you will see these prairie potholes. So, and they formed, these huge potholes formed because as Glacial Lake Agassiz released, all this water rushed down the St. Croix River Valley, cutting it out. But we had huge boulders that would get caught in divots and then start grinding. And so some of them look like cannonballs. They look almost perfectly round. If you go into the visitor center, obviously probably not right now with COVID, or if you're watching this later, you might be able to go. They actually have some of the eroded rocks, the smooth polished rocks that they found at the bottom of these. They're huge. This is like 2-story high one there. So retreating glaciers also form featured called kettles. And a kettle is a small depression that forms when chunks of ice in the glacier melt. And there's a big chunk of ice in the middle of the till, and the till settles all around it. But where the ice melted and they didn't have as much till, it left a depression because as everything else settled down and the ice melted, there was a hole. And those holes become kettle lakes. When the ice melts, guess what? It fills up the kettle. And you can get that in modern day. This is a glacier that has retreated, and as the glacier retreated and melted, it dropped all this till, but there are depressions where there was more pure forms of ice without as much till, and it left a depression. So, other landforms that glaciers can include are fjords, which you think of, if you think of a fjord, you think of Norway. They're long, narrow, deep inlets in the sea between high cliffs. And it's, as in Norway, Iceland, they typically formed by submergence of a glacial valley. So, in other words, a glacier came and scoured this out, but as sea levels rose, the sea level infiltrated the valley and flooded it, and that's a fjord. It's a flooded glacial valley. Cirques are interesting. They are bowl-shaped regions at the top of the glaciers that are formed by melted ice. So as this breaks away, they're really knife-like shapes along here. So this is a cirque right here. This is a small, teeny tiny cirque. This is a separate cirque. So cirques separate different headwaters of glaciers. And as they erode away, they're really sharply peaked areas. These glaciers are helping form these peaks too. And it's their accumulation. So as they flow together, look here, this cirque flows into this main thing. This little teeny tiny cirque flows into this. So the main valley has an accumulation of all these little cirque areas coming in. And there's an assignment that you may have done or are about to do where you're going to have to identify these different features, and that is on the test. So make sure you spend some time. You've got multiple attempts. That's a good thing to practice. Because I may do different pictures on the test than in this practice. I mean, they'll have the same idea, but we're there. Horns then are sharp peaks formed when ridges are separating 3 or more cirques. So there has to be 3 or more sides. So it's not just going down this side or this side, it's 3-sided or more. And you can see that here. We've got one side here where the glaciers flow down this way. Then you've got this second side, and there obviously needs to be at least a third side on the back, but you could have 4 or 5. It just depends on the direction from which that goes. But when you've got one peak that can send out in more than 2 directions, 3 or more directions, that's called a horn. All of these individual bowl-shaped areas that are divided by sharp ridges, those are called cirques. So arêtes arête is that thin knife-like thing. So on my cirque here, there's these sharp things are called arêtes. So it's a thin, almost knife-like edge of rock, which is typically formed when 2 glaciers erode parallel U-shaped valleys, and the arête is a thin ridge of rock that is left separating the 2 valleys. Hence, it's also separating our cirques. These are arêtes. Here is an arête. Here's a valley glacier on this side. Here's a valley glacier over here. It's eroding away this side. It's eroding away this side. That sharp area is what's left between them. Drumlins are a deposit as a glacier melts, and you will see these too in Minnesota. They are low oval mounds or small hills, typically in one of a group, so there tends to be many of them quite often. They're consisting of compacted boulder clay molded in past glacial actions. Okay, so what it's also going to show you is the direction of movement. And so there's usually a really narrow side and a really humped up side, and that shows you the direction in which it was pushing and moving away. Glacial lakes. A glacial lake then is simply a lake that originates, its origins come because it's at the end of where a melted glacier is coming from. So as water melts from the glacier, if there's a lower depression at the bottom of it, that's a glacial lake. My parents and my sister had gone to Alaska to visit my cousin, and they took like a ferry or a cruise on this glacial lake. And there was somebody out on a kayak, and the person, and it's usually like the parks departments that run this, and they yelled to the guy, "Can you hear me?" And he said, "Yeah." And they said, "Well, why did you ask him that first?" Because they said, if we give him instructions, then he pretends he can't hear us. If we know he can hear us first, then we have our confirmation that he's going to get the directives. And they said, you have to get off of this lake. It is too cold. You will not survive it if you flipped. It is not legal to actually kayak on that glacial lake in that part of Alaska because it's just simply too cold. So they are formed when the glacier erodes the land and then melts back and fills in that hole or that space that has been created with water. That's a glacial lake. U-shaped valleys are just that. What do you think a V-shaped valley is? It's a river cutting down, so it's really steep on the sides. A U-shaped valley is more trough-like. So it's a glacial trough is formed by the process of glaciation. Its characteristic U shape with steep, straight sides and a flatter bottom tells you it was probably a glacier coming down there. If it's a V-shaped valley, it was probably water cutting, and that's more of a river action. So continental glaciers even created some of the Great Lakes of North America. If you get a chance, this was a student project that I found, and it goes into the creation of the formation of the Great Lakes, of some of them. And so if you're really interested in that, go ahead and take a look. But here is a quick quiz. Are you ready? The answers are literally written here, so this shouldn't be too bad. We have a glacier that's retreated. This is meltwater. It's a meltwater stream. You can see drumlins down here. We see a moraine. Here's the terminal moraine. If you look on the side somewhere, we could probably see some lateral moraines. So this would be more of a picture where I would want you to identify like meltwater and maybe a moraine. It doesn't have really good lateral moraines, but it has good drumlins. How do glaciers form? Well, I'm not asking you this question in essay form on the video, but I might ask it in a multiple choice, so pay attention. Maybe. Here we go. I hope. Snow accumulates in cold climates to form snowpack. So we got the snow falling. It builds up over the course of the winter. The glacial ice to form, the amount of snow packed must grow over long periods of time and not melt as much as it begins. So this is the beginning of a glacier. It builds over time, meaning that snowfall must exceed ablation each year. That is, on average, it needs to gain more than it loses. That's what ablation means in geologic terms. So we've got our glacier forming, and eventually it will start to flow under its own weight. Once it reaches about 50 meters thick, it can start to flow. Year 10. It takes a long time. Meltwater from the surface snow percolates at the base of the snowpack. It also kind of makes it slide easier down. So as it melts down here, it can actually have some friction melting it. And you can actually have pockets of ice that make a glacier kind of bendable. And you can get plucking. After 2 or more years of snow, the surface starts to condense, forming small bits of ice-like things called firn. Over time, the firn develops and continues to condense more and more until it forms ice. So we've got ice forming down at the bottom and snow falling and compacting. We have glacial ice. We've got enough depth. Now, once it reaches about 50 meters thick, it can start to move under its own mass. This says 60 to 90 meters. On the test, we're going to say 50. Now it's starting to flow under its own weight, and it's creating that U-shaped valley. It's eroding it away through abrasion and plucking. Glaciers can surge 40 to 60 meters per day due to increased snowfall, or an earthquake shattering can force it down. Snowfall equals ablation, then the ice front stalls. Doesn't move forward, doesn't move backwards. But if it exceeds accumulation, the ice, so in other words, if more melts than we get, then it's going to retreat. So remember, the terminal moraine is the furthest point the glacier made it. So here's our terminal moraine, here's our meltwater streams, here's some glacial lakes. And oftentimes the outwash plain occurs in front of the terminal moraine, where the glacier meltwater deposits sand and gravel sediments. So there's our outwash plain. The glacier melts, revealing the eroded ground beneath it. We can start to see striations and all that to tell us where it went. You can go watch the rest of that if you need to look through, but I'm probably going to stop this and ask some questions now. Okay, I think I do want to watch this. So this is Greenland ice sheet. It's over 200 kilometers long, and its front's almost 6 kilometers wide, and it can flow as fast as 30 meters in a day. The instruments were installed in 2010 to monitor the front of the glacier, and they witnessed, and this is why I want to show this, one of the largest calving events to happen. So in other words, 4,000 meters across, this whole front is about to break off. And there it goes. That was a massive amount of ice. 4,000 meters across, and the whole front broke off. And I think there's one more. I don't want to fast forward, I don't want to miss it, but I also don't want to waste our time either. You can see, by the way, icebergs are not something you want to like kayak up to and get onto, because they are unstable and they tend to flip. And if you're on the top of it and it flips, you're going down with the iceberg. There goes another piece. I thought there was another good event that happened on here. You can watch more if you wish. Probably going to ask you questions about calving. All right, this is a much better picture to ask you questions of on a test. This is a receding glacier. Here are some, what are these features called? That would be meltwater what? And we have some eskers coming out. These were the streams coming out. And if we look far enough up here, we could probably see a moraine, but it's not great definition. But for eskers and meltwater streams, if they were going farther, or the glacial lakes, yes, this would be a good question for that. This shows you the retreat of a glacier over, well, you'll see the timestamp. This is February 2010, and it's showing you in lines for each month. And you see how far back the glacier is retreating. It's still surging forward and melting, but it is definitely retreating. Now we're in April. See how much is receded in just a few months from February to April. It's lost that much of its forward motion. It's receding. We had a little movement forward, a little surge back, but basic recession is what we're seeing here. Now we're to September, it's receded back even more. And as I fast forward, we can see that it's continuing to recede back, not quite as fast now, but here is January of 2011. So this is about a year's worth of difference that we lost of that glacier, and that's pretty common in most of our glaciers around here, that we're losing many, many feet. This is in the notes. I'm not taking it out. You do not need to go into the notes and answer these questions. If you're really bored and want you to practice for the test, that's completely fine. They would normally have been stuff we would have done together in class, and obviously we're not doing that, so we're doing the visual.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at ice ages. In 1840, Swiss scientist Louis Agassiz noticed glaciers. Huge rivers of ice created by snowfall occur throughout northern Europe. As glaciers move, they transport rocks and scour the ground beneath them, leaving evidence of their passing. Agassiz theorized glaciers were the remnants of huge glacial ice field that once covered much of the continent. Geologic evidence of massive glacial activity also occurs in North America. Agassiz had discovered evidence of the most recent major ice age, a period of time when glacial ice fields extended across large sections of the planet. Geologists have evidence of 5 major ice ages, more properly called glacial ages. The earliest well-established glacial age, called the Huronian, formed between 2.4 to 2.1 billion years ago, during the early Proterozoic eon. The last glacial age, and the only one to occur since humans appeared, began 1.5 million years ago and receded 15,000 years ago. During that time, the Laurentide ice field covered all of Canada and extended as far south as Indiana. Glacial ages have enormous effects on the planet's weather patterns, animals, and plant life. Animals that cannot adapt to the colder environments die out. Similarly, animals that adapt to cold environments may not survive the change when glaciers recede. The Milankovitch theory by astronomer Milutin Milankovitch suggests variation in the Earth's orbit account for glacial ages. Instead of orbiting the sun in a constant pattern, the Earth wobbles. Over millions of years, this wobbling affects global temperatures. As glacial ice fields spread, snow and ice reflect sunlight that would otherwise warm the Earth, causing further drops in cold temperatures. Low levels of carbon dioxide in the atmosphere can also contribute to a glacial age. As you can see, Earth's climate goes through drastic changes when looking at it over thousands and millions of years.
Okay, we're almost done, I promise.
Earth is the only planet that contains water.
Okay.
Glaciers of the Earth.
So there's some
5,000
good
meters.
pictures in here, but it's a review. If you want to go back and look at that one to go over what I've already said, go for it. I'm not going to spend time on it right now. I did obviously have a bunch of questions from it, but the biggest one is I might actually make a little bit of something in here because there are some things in here that I want to make sure you know about. Like, where can you find ice sheets today? You should be able to know that you can find them in a continental glacier you'd find in Greenland and in the Antarctic. You'd find alpine glaciers in Alaska, in Yosemite, in the Alps. You would find sheets of ice that would be like the North Pole. And the zone of point where it's cold enough to get a glacier, that's our cold zone. And so basically in East Africa, there are glaciers in Africa. If you go high enough up above the snow line, the point at which snow can form. If you go to Hawaii, you can go in the ocean one day and be skiing up in the mountains on another day. I would not recommend going on the mountains one day and then going scuba diving. In fact, they'll ask you and make sure you don't do that because it's too much pressure change difference. But that's kind of the bigger points of what I want you to know from there. And this is a video, if you want to go back and watch it, you're welcome to, on global glacial retreats. Normally we would do this in here. This is the picture that will be on your test. You need to, if you want to go in the notes and practice this, go for it. I'll put unlimited attempts on the notes, but I am not going to go and correct the essay questions, so just know that. Do not bother with that. So if we look here, we've got our eskers, our meltwater streams. Here's a moraine, but this is our terminal moraine, the farthest with which it would have gone, the oldest one. This would be the newer moraine. Here are my drumlins. This is our meltwater streams. This could be considered a glacial lake if you wanted to, or a kettle lake. So here's maybe some start of some, it might have been a lateral moraine. If it was connected all the way through, I would have called it that. I wish I had a picture, I guess, that had a lateral moraine. So maybe I'll get a picture similar to this one. It might be this one. And this is the recession of the glacier. So kettle lakes, meltwater streams, oldest terminal moraine, youngest terminal moraine, drumlins, and eskers. And congratulations, you made it to the end of the notes. So really what you need to remember with glaciers is it's a form of mass wasting that is caused by ice. And the whole thing that causes it to move is gravity pulling it down, whether it's being pulled down from a mountain or it's a continental glacier where it just ends up getting so much weight that gravity pulls it down and it pulls it out in all directions. In fact, our glacier that was in Minnesota actually originated in Hudson Bay. In fact, the earth is so deformed, the lithosphere was actually under so much weight with those couple miles thick of ice originating there and flowing out in all directions. It created the depression that is now Hudson Bay. And the asthenosphere, the lithosphere, is actually rebounding. And so Hudson Bay is actually getting shallower every year. And it's quite, I think it's almost a foot a year that it's getting shallower, which will be a problem because Hudson Bay is a pretty big waterway to get goods and things through ships. So gravity, erosion, mass wasting, all are contributed to gravity and stuff wanting to flow downhill. And that movement of things is erosion. The specific type of erosion we talked about today is glacial movement or ice movement and how it erodes. And remember, the two pieces of evidence are glacial striations, and how it erodes is striations, that sandpaper effect, and plucking. As always, if you've got questions, please email or Zoom with me, and we will get you figured out for whatever you need. Have a good day.